why does a magnetic field changing create electricity? This is a law that makes nearly every modern electrical device work. So before we talk about the law, we need to clarify one concept. It is magnetic flux, which is represented with this symbol. And we did look at this in Gauss's law, but what it is the amount of field that passes through an area. Mathematically, it's given with B, A, cosine, and B is the strength of your magnetic field going through. A is the area of your surface or your loop. And this angle is the angle between your field and the normal. The normal is the perpendicular. So when the field is going straight through the loop and cosine equals 1, that is maximum flux. If the field is parallel to the loop, flux is 0. And now I've talked about flux a little bit, we can look at Faraday's law. Here is Faraday's law. It says that EMF is caused by changing flux. So this here specifically induced EMF or voltage. Change in flux is change in magnetic flux. Change in T is the time interval over which our flux is changing. And the reason why it's negative comes from Lenz's law. And we're going to look at this next. If flux through a loop increases or decreases, this loop will fight back by generating a current. So if your field changes, if your area changes or your angle changes, this all counts as a change in magnetic flux, which means we can induce EMF by doing one of these three things: increasing the strength of the field, changing the area of the loop, so stretching it, or rotating the loop, which will change the angle. Here's an example problem. A square loop with a side length of 0.4 meters is placed inside a uniform magnetic field of 0.20 teslas. Let's solve for three things. First, what is the magnetic flux through the loop when the field is perpendicular to its surface? 2, what is the flux when the field makes an angle of 60 degrees with the surface? And finally, if the loop that our field is passing through is rotated from 0 degrees to 60 degrees within 0.1 seconds, and it has a resistance of 0.15 ohms, what is the induced current that comes from this? Let's go through this step by step. So first, how do we find the flux when the loop is simply perpendicular? Every single formula we're going to cover in this video is on the free cheat sheet in the description, and we can use them to solve this problem. So first of all, let's find the area of our square loop. Since the length is equal to 0.4 and it's a square loop, then the area is length squared, which is 0.16 meters squared. We need this for our flux formula, which is B area cosine. So that's why I found the area. Plug in our value. So the strength of the electric field is 0.2. The area we just found is 0.16. And cosine of the angle. What angle is happening here? It's at 0 degrees because it's perpendicular. So there is no angle with the normal, which means it's maximum flux. We don't have to consider cosine because cosine of 0 degrees is simply 1. Now, we can find our answer, which is 0.032 Webers. And Webers is simply the unit that we measure flux in. Great. What about our flux when our square loop is angled like that? So now the normal, which is perpendicular to the surface, looks something like this, which means it's going to create an angle 60 degrees with our flux. So instead of cosine 0, it's now cosine 60. That's the only change. Everything else stays the same, and our answer is 0.016 Webers. Now for the final problem, which was finding how much induced current comes from this rotation process. This is slightly trickier. I'll walk you through it. So first, we have to find the change in flux. The change in flux is given by the flux at one point subtracted by the flux at your next point. Remember what our rotation is. We go from 0 degrees to 60 degrees. We actually found the amount of flux for both of those angles in those first two problems. So the flux after this rotation is the flux at 60 degrees, which we found as 0.016, minus the flux initially, which is flux at 0 degrees, and we found this as 0.032. This is equal to negative 0.016 Webers of flux. So we know the difference in flux between our starting angle and our finishing angle. How about the time interval? The time interval is 0.1 seconds. Now, how do we go from this to the amount of induced current? We're going to find current using Ohm's law, which is voltage, or EMF here, divided by the resistance. This means that we're going to need to find the EMF. An EMF given with this formula, which we were looking at the start of this video, change in flux, divided by change in time. And it's the absolute value. So change in flux, negative 0.016, but since it's absolute value, we don't care about the negative. Divided by the time interval. This gives us 0.16 volts. This is the induced EMF that comes from our rotation. Now from this EMF, let's plug it into the Ohm's law formula, which is going to give us the amount of induced current that comes from our EMF. So 0.16 divided by the resistance given at the beginning, which is 0.015. And the final answer is 10.7 amps of current. When we turn our square loop of wire through this uniform magnetic field, this is how much current comes from it. This was Faraday's law of induction in action. When we change the angle, the current changed as well. We gained this much current. Now moving on to Lenz's law. I did mention Lenz's law earlier. And what Lenz's law is, it tells us that the direction of current is not random. It's given by Lenz's law, which says that the induced current opposes the change in flux that caused it. I'll say that again. The induced current opposes the change in flux that causes it. Before I show you visually, let me explain two symbols. We have this and this. This means going into the page or into the screen. This means coming out of the page toward you. If the field is increasing into the page, so here's our field, it's going into the screen, forward, and we have our loop here. This is where the field's going through. The loop creates a current that creates a field that comes out of the page, the opposite direction, to fight the increase in field going through. This explains why in Faraday's law there's a negative sign, and it also explains why the induced current fights the change, not the field itself. And if you use the right-hand rule and a bit of logic, if flux is increasing into the page, then the current of our coil is going to be clockwise. If the flux is decreasing into the page, then the current is going to go counterclockwise. Now here's something interesting. You don't even need a full loop. A moving conductor inside of the magnetic field can generate voltage. And the formula to represent this is EMF equals B L V, where B is magnetic field, which is perpendicular. L is the length of your conductor, and V is the velocity that is moving it. This is derived from Faraday's law. What this means is, imagine we have some field, and our field's coming out of the page. And our moving conductor is this, and the length is this, and the velocity is this. What it does is it cuts through these field lines, and the charges get separated. And when the charges are separated, voltage appears. Before we wrap up, there's one last result you should know. If a moving rod that's going through a magnetic field produces a force on the charges via this formula, which we looked at earlier, then that motion also implies that there is an induced electric field in the region, not just an induced EMF. And since electric field is defined as force per unit charge, and force is equal to charge velocity magnetic field, an electric field is equal to velocity times the magnetic field. So a changing magnetic flux doesn't just produce a current, it produces an actual electric field. And to summarize everything we talked about in this video, a changing magnetic flux induces EMF. EMF depends on how fast and how much this flux changes. This is what Faraday's law is. Lenz's law tells us which way the current goes, which is always to oppose the change. And moving conductors can also generate EMF without rotating and without looping.